Okay, so welcome back. So now that we have an understanding of sample space, we can look at how we can find probabilities using those sample spaces. So the first thing we should do though is look at some of the notation. So we're going to be using a capital P for probability. So anytime you see that, think probability. And then A, B, and C will be denoting specific events that we're looking at. And then, so putting it all together, we have the probability of A denotes the probability of event A occurring. So anytime you have that type of symbolism, it's the probability of that event. Okay, so the first type of probability that we could have would be the relative frequency approximation of probability. So we conduct or observe a procedure and count the number of times that the event A actually occurs. Based on these actual results, the probability of A is approximated by the number of times A occurred over the number of times the procedure was repeated. Okay, that's nice, but what does that mean? Well, let's look at an example. In a recent study of 1,450 adults in New York, it showed that 843 of them drink alcohol at least one day a week. Find the probability that a randomly selected adult in New York drinks alcohol at least one day a week. So we don't have all of the data that we could possibly, or that we need to in order to answer this question accurately, but we do have some sample information. So we do have a sample of 1,450 adults, and out of those 1,450 adults, 843 of them drink alcohol at least one day a week. So we're not going to be able to give the true probability in this case because, again, we don't have all the data, but we can approximate it. So that's what this is kind of relating back to. This type of probability is working with sample information. So if we want the probability that drinks at least one day per week. So that's what we want. And so the number of times A occurred, so there was 843 of them out of the 1,450 that we surveyed. So let's just get a calculator out to get a little bit better value of that. So 843 divided by 1,450 equals 0.5813, blah, 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 blah. Okay. Now, as far as number of decimal places with probabilities, you're going to want to use a minimum of 3. Some cases they use 4, but for right now, we're going to use 3. And we're going to get a little bit more specific about that number of 3, because if we get to really small ones, we're going to have to rethink that a little bit. So we'll get into that in a little bit. Okay, but this is the idea. So anytime you have sample information, you can approximate the probability. We can't get it truly because we just don't have all the data. So that's one. The next one is the classical approach to probability. It requires equally likely outcomes. So if a procedure has n different simple events that are equally likely, and if event A can occur in s different ways, then we put the number of ways A can occur over the number of different simple events. So it's similar to what we saw before, but the only major difference is now we do have the population. So for this example, the sample space determined by a couple who has 3 children is that boy, 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 girl, girl, or excuse me, boy, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. And that's it. There's no other possibility. So that's the entire sample space. So that's the population. So now, if we assume that girls and boys are equally likely, even though technically they're probably not, we're still going to be able to get some truly accurate probabilities from this. So the probability of getting exactly one girl, and there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So we know automatically it has to be out of 8. But how many of those have exactly one girl? There's one outcome. There's another one, and and then there's another one, and that's it. So there's 3 of them that have exactly 1 girl. And we can divide that on a calculator pretty quick to get 0.375. So 0.375. Nice, right? Now what about 2 girls? We still got it out of 8. 2 girls, 2 girls, 2 girls. So it looks like 3 again. So 0.375. And what about all girls? There's only 1 of those, right? So 1 out of 8, or 0.125. So out of these 2, obviously we like the classical approach better because, again, you have the entire sample space, so there's no guesswork in there. You're not approximating anything. It's the true probability for those different outcomes. All right, so that's 2. The third one is the subjective probabilities. And if you know what the definition of subjective means, it means you're guessing. So the probability of A is estimated by using knowledge of the relevant circumstances. So when trying to estimate the probability of receiving snow tomorrow, meteorologists use expert knowledge and computer simulations to estimate the probability. They guess. So here's one for you. What is the probability that you will get stuck on the next elevator that you ride? Now, most people would probably say there's probably this big of a chance, very small chance that it's going to happen. But you might have somebody that just has a lot of bad luck. It says, I know 100% that I'm going to get stuck in that elevator. But again, it's subjective. It depends on the individual in that case. So I wouldn't get too anxious or worried about seeing these types too often in the homework assignments, but you do have that case though. So let's try another one and see if we can kind of figure out those probabilities. Refer to the sample data in the table below that represents the number of dogs and cats at an animal shelter. If one of the animals from the shelter is randomly selected, what is the probability that it is a dog? What is the probability that it is a female cat? So they're taking all the animals and they're putting them in a big sack, and then you're just drawing one out randomly. It's kind of hard to put all of them in the sack, I know, but that's kind of the idea. Now, where do we start? If we want to create a probability, we got to know how big the sack is. How big is our sample space? So let's take a look at what we got. We got some male dogs and male cats and female cats. Well, we got to just add them all up, right? We got to see how many animals we have in the shelter. Now, you could add it either way and get to your sample space value. So if we add down, we get 47. If we add down here, we get 52 for a grand total of 99. And if we add across, well, we got 48 there. And it looks like 51 there, and that also adds to 99. So that's always a good check, is to add both directions. You might need some of those numbers anyways. So if you add in both directions, you should get the same result. So 99 animals is in our sample space. 99 unique animals. Okay. So now let's answer the first question. What is the probability that is a dog? Now, it doesn't say what gender. It just says a dog. It could be male, could be female. So there's 47 dogs in the shelter. So 47 dogs out of the 99. And if we divide that on a calculator, I think it is 4747. Yeah. So we got a lot of 4s and 7s. So this should be 0.4747 ... Now, if we're rounding it to 3 decimal places, make sure you don't just chop it off. Round it up if you have to round it up. Round it down if you have to round it down. So 0.475. Now, what about for a female cat? Well, a female cat, there's only 29 of those. Now, a common mistake is that people want to take the female cat out of all the cats. So that people would want to say 29 out of 52, but that's not correct. Because the question wants you to just take one animal out of the entire shelter, not just out of a subgroup of the cats or a subgroup of the dogs or something like that. So you still have to take it out of 99. So if we got 29 out of 99, 0.292929, and so on. So in this case, 0.293. All right. So these questions are a little bit nicer because, again, you're dealing with a concrete sample space, so you get concrete probabilities from them. All right. So we'll pick up more in the next video. See you in a minute.